A 45 kilogram sign is attached by two strings as shown in the diagram, and we have to calculate the tension T1 and T2 in the coils. So we are going to see the angles. You can see alternate interior angles, 50 degrees and 35 degrees. So these are equal to each other. Now we are going to draw a free body diagram for the attachment point. Tension 2 is at an angle of 35 degrees up the positive x direction, and tension 1 is at an angle of 50 degrees up the negative x direction, and the third force is the weight of the sign. It's going directly downwards, and we are going to complete the vector triangle for the tension 2 and tension 1. The x component of tension 2 is going right, y component is going up. The angle between the x component and the tension 2 is 35 degrees. And we are going to do the same thing for tension 1. The x component is going left, the y component is going up. You should know this from chapter 3 when you were doing 2D kinematics. You resolve the initial velocity into x and y components by drawing the vector triangle. So that's the same thing we are doing here. Now let's look at the knowns and unknowns. We do know the weight is equal to mg, and the mass of this sign is 45 kilograms. So we have defined the coordinates, right as positive, up as positive, and we are trying to solve for tension 2. Tension is a force, the unit is newtons, and tension 1, again a force, unit is newtons. So the positive or negative sign is not a clear way to indicate the direction for the tension force. The direction is indicated in the diagram using angles. Now let's see the applicable concepts. This is section 4.5 in your textbook. Now we are going to plan a solution, and we are going to start by looking at each force. So tension 1 has x component, and it's negative because it's going to the left. And the y component of tension 1 is going up, it's positive T1y. The x component of T2 is going to the right, so it's positive 2x. And the y component of T2y, it's positive going up. The weight does not have any x component. The y component is negative because it's going directly downwards. And now we are going to use Newton's second law. And we're going to use the component form of the Newton's second law. One equation for the net force in x direction, and another equation for the net force in y direction. Now I'm going to look at the net force in x direction, and acceleration in x direction is 0 because the system is stationary, it's not moving. And if you look at the chart, you can see the x components, the negative T1x and positive T2x. So that's equal to 0. T2x minus T1x is equal to 0. And I'm going to express T2x and T1x in terms of cosine of the angle. T2x is T2 cosine 35, T1x is T1 cosine 50. And I use the knowledge on trigonometry to get an expression for T2x and T1x in terms of cosine, because T1x and T2x are on the adjacent of the vector triangle. Now let's solve for T2 in terms of T1 cosine 50 divided by cosine 35 is equal to T2. Now I'm going to use again the Newton's second law, the equation in y direction, and net force in y direction is equal to mass times acceleration in y, and acceleration in y direction is 0. Again, for the same reason, the system is stationary, it's not moving. And I'm going to look at the little chart now, and I have to consider T1y, T2y, and negative mg. So those are the components of forces in y direction. So if you add all those components, that's again equal to 0 because acceleration is 0. And now what I'm going to do is I'm going to express this T1y and T2y in terms of the sine of the angle, because T1y and T2y are the opposite of the right triangle. So now I'm going to substitute for T2 in terms of T1, and T1 sine 50 plus T2 is T1 cosine 50 divided by cosine 35 times sine 35. Do not forget sine 35. Minus mg is equal to 0, and that is T2. That's the substitution I did for T2 in terms of T1. Now I have just one equation and one unknown. The unknown is tension 1. I'm going to factor out tension 1, and it's common for both terms. When I factor out a T1, and that's what I get, I'm going to add mg to both sides of the equation. Now I have just mg on the right hand side. If I divide both sides of the equation by this expression, I get tension 1 is equal to mg divided by sine 50 plus cosine 50 divided by cosine 35 times sine 35. So now you have to solve for tension 1. When you put this sine 50, cosine 50 into your calculators, guys, please make sure that your angle is in degrees, not in radians. Please check that in your calculator settings. And then since I have T1, I'm going to substitute for T1 in the equation for T2. That is just 363 newtons. And when I do the substitution and after I put these numbers into calculator, I got 285 newtons for T2, and for T1 I have 363 newtons. Now is the solution complete? Yes. Is the sign of the answer correct? Yes. Correct units and then magnitude is reasonable. We started the question by drawing a free body diagram, and then we completed the vector triangle and looked at the x and y components, and we identified the unknowns, and we completed this chart to identify the x and y components of each force, and we used Newton's second law, the component form, for the x direction and y direction. You can see initially there were 4 unknowns, but then it reduced down to 2. So that's it.